start the challenging.
We would like to challenge Rocky Bottom.
Please. Number 10, a rocking bottle. Is that right?
Yes.
We accept.
Okay. The rocking bottle has been accepted. So we have 5 minutes for preparation. Could you please write your name down?
Good morning, ladies and gentlemen. My name is Ginsberg from the Brazilian team, and I'm going to present problem number 10, the rocking bottle. The problem says, fill a bottle with some liquid, place it on a horizontal surface and give it a push. The bottle may first move forward and then oscillate before it comes to rest. So let's investigate this phenomenon. First, I'm going to my theoretical formulation, then the experiments, the comparison between the theory and the experiments, and the conclusion. I would like to start defining center of mass. Is the average of the positions weighted by the mass. We can define this for any object, like this we show, and for the bottle as well. And here is the general formula of this definition. Moment of inertia is a measurement of an object resistance to change to its rotation, and is given by this formula, where ρ is the density, r is the distance to the origin, and dV is the differential of volume. And torque is the tendency of a force to rotate an object about the next. And it's given by this formula, where E is the moment of inertia and alpha is the angular acceleration. Viscosity is fluid resistance to shear stress, and shear stress is given by μ, that is viscous coefficient, U, that is velocity, and Y is the coordinate. The oranges are in the intermolecular forces and the transfer of molecular momentum. And here we can calculate velocity profile for some flows. There is a friction associated to viscosity, and in the range we use it for water, engine oil, and glycerin, this is the main dissipative force. And we can have 3 asymptotic cases. First, the infinite viscosity, when the liquid can be approximated to a solid, the zero viscosity, when we will not have oscillation, and the non-Newtonian fluids, when the period won't be constant. In the first case, there will be no dissipation due to viscous forces, because the characteristic time of sliding between each fluid layer is way bigger than the rocking itself. The torque is not uniform along the movement, but in the final oscillation, the movement is basically underdamped and the restorative force is the torque. The dissipation will be mainly by the air and the ground surface. In the second case, we will have no dissipative force due to the fluid, only due to the ground and air as well as in the previous case. The fluid inside the bottle will be in continuous motion to the contrary direction of the initial push. And there will be always a torque direct to the motion, and there are no restorative forces. In the third case, this mathematical analysis is very complicated because the viscosity varies with kind and the velocity of the flow. We analyze this case with water, engine oil, and glycerin. Here we can draw a force diagram. Omega is the angular velocity. W is the weight of the liquid mass. We have the friction with the ground, the distance to the center, and can calculate this torque, given by this formula. The inertia of the liquid. When the dissipative forces cause the bottle to stop, the fluid continues its movement because of the inertia. So we have a movement in one direction causing a torque. In this torque causes the movement in the contrary direction. This happens until the bottle comes to rest by the dissipative forces. In our experimental procedure, we add fluid on the bottle, push it with a robot, so we have a constant initial velocity that we measure every time, film the movement, and analyze the rocking. Here are our materials, and here we can see a video with a bottle filled with water at 10%. We can see this final rocking. And we can also see movie with 20% of water inside the bottle. we can see that these oscillations are not linear. We have two kinds of oscillations. First, the water oscillation, and then the fluid oscillation. So this causes a non-linear oscillation. From these movies, we can draw a graph, and with 30% of the ball filled, we can see that these periods are not constant, nor the amplitudes of the movement. So we cannot approximate it to another depth. And here we can see another graphic of 20% filled, water filled. We can see that this looks like another depth graphic. But if we calculate the periods, we will see that they are not constant and they are smaller after each oscillation. Here we can calculate the average period of this oscillation, and we can see that it gets smaller as we have a higher percentage of bottle filling in the same temperature. We can make another depth analysis. In general, we have this equation for the movement, where x is the position, beta is the dissipation coefficient, and omega is the natural frequency. And so for x, we have an equation of this kind, where a is the amplitude, tau is the characteristic time, and phi is the phase of the movement. And we can also make this experiment with engine oil. We can see that these oscillations look more periodic, and we can make a graph analysis of this movement. We can calculate the periods by the graph, and we see that they get smaller in every period they are. So this we can see from this graph that the error from the underdamping approximation is very high. So we conclude that it's only a first approximation, but it's not a good one. This is caused by the non-linearity of the term with the viscosity that varies with other powers of the velocity. We would have an equation of this kind, and this causes the non-linearity of this equation. We can calculate also the dependence of the period with the viscosity for the engine oil. We can see that higher the temperature, higher the period. And we can also calculate the viscosity of this fluid. And the final distance varying the temperature with water and oil. From this graph, we can see that the main dissipative force in these two cases is the viscous force. Why does it happen? When we have a higher temperature, we have a lower viscosity. So the dissipation due to viscous forces will be lower, and the final distance will be higher. We can see that also the variation of the density of these fluids is not very relevant. So as we kept the same mass of fluid and the same initial push, these data are correct. We can also do an experiment with glycerin. We can see that there are no oscillations. Why there are no oscillations? Because of the high viscosity, we have a high density parameter. So we would have a best approximation for an overdamped oscillation. So the graph would be just a fall with no final oscillation. And we can also do the experiment with sand. Why would we do the experiment with sand? Because the viscous forces would be so high that the shape of the fluid would not deformate. So we would have a really good approximation to an underdamped oscillation. Here you can see our approximation, and the period we can calculate from this is basically constant, and the deviation from the average is very, very low. So it is a good approximation, to have the underdamped oscillation. Here we can calculate the average period variating the percentage of sand, and here we can see the graph. We cannot calculate the tendency, but we can explain this experimental data, because as we change the percentage of the bottom fluid, we also change the center of mass, and therefore we change the torque acting on the bottom. So we change the restorative force. These are current because as we change the center of mass, we put more sand in the bottom. We change the center of mass to higher in the vertical coordinate, and then we have a bigger torque. Therefore, we have a bigger mass. So we have a bigger period. From this, we can calculate the relevant parameters. There are the percentage of the bottom filled with liquid, the viscosity of the fluid. We have the asymptotic case. If it's too big, the time of sliding between each fluid layer is also relevant. If the viscosity is equal to 0, the analysis is done by energy, and there are no restorative forces. The temperature is relevant because we change the viscosity, changing the temperature, and this changes the energy dissipation. The density is also important because it changes the moment of inertia of the bottom and also changes the torque. So in the conclusion, the movement is due by the torque caused by the fluid. The inertia of the fluid plays a key role in this phenomenon. The viscosity is the main dissipative force for water, glycerin, and engine oil. We have another damped oscillation when the fluid can be approximated to a solid. And the period depends on the temperature and the percentage of the bottom fluid. Here are our references, and thank you very much for your attention.
Thank you. Questions from the opponent?
Thank you for the presentation. Can I look at your slide where you have your equation of motion for the bottle?
Sure.
Yeah,
Which one?
you have the mx double dot plus kx dot plus minus kx or something like that. Your equation of motion for the bottle is a simple damped oscillator. Yeah, this one. So this is your equation of motion for the bottle, is that right?
Only for when can approximate to another damped oscillation. That is,
so this
sand.
goes for liquid. If you fill the bottle with a liquid, does this equation apply?
Only if the liquid is ideal.
Ideal. So that includes water?
No, it doesn't.
No. Okay. So which equation of motion will then describe the bottle's motion for if we fill it with water?
We will have a higher term depending on the velocity.
Oh.
We cannot calculate this analytically.
No analytic solution. Then do you have a graph, a numerical solution?
No.
A theoretical graph, motion time graph.
We can't because we can't know the. We can know the dampness of the viscosity with the velocity. As we have different initial conditions, we will have
so you
different
don't have
dampness.
So you don't have any examples of your theory position time graph for the bottle?
No, it's we have
okay.
different initial conditions.
Yeah, okay, we can talk about that later. About your experiment, right? You conducted it on the table, right? Is that right? You push a bottle on the table.
In the floor with a robot.
On the floor.
Yes.
Did you check how flat was the floor? As in, did you make sure the floor was flat
Yes,
and horizontal?
I made sure.
Okay, can we look at some of your experimental data, your graphs? Or maybe you can do that later. We are running out of time. Yeah, thanks.
This one or this?
Leave it over.
Yeah, we will talk about that later.
So 3 minutes for you.
About your motion, your equations of motion. How you expect? Okay, let's just go to your simplest one. The one where you have a KV damping. Yeah,
when I have the liquids I use, we have other powers of of the velocity that depend on the dissipation. So we will not have that equation exactly. We have that equation when we have ideal fluids, that is, the viscosity does not vary with the velocity.
Viscosity does not vary with velocity.
Most
liquids are like that.
no, not in the range.
What sort of liquids do you have in mind?
We could reuse the water, the glycerin.
It applies for water?
No,
it does not. Okay.
Because the viscosity is very low, so we have chaotic movement.
Okay, can we look at, do you have any motion time graph at all, or like the simple case where your damping is proportional to the first power of the velocity?
I can draw the graph. I don't have it.
Okay, please do. Yeah, so it is decreasing amplitude.
Yes, and the period is the same.
Okay, so do you have any experimental graphs that look like this?
Yes, I have the same one.
Yeah, do you have a look? This is with sand. Do you have something where we fill the water with a liquid that looks like this?
No, because we have to have a very large viscosity, but we could not find this liquid in our...
Okay, if you need a very viscous liquid...
I could use glass. That is basically
you could use... glycerin is quite viscous, right?
Because in the range of the viscosity of glycerin, we have a ducting parameter very big, so the fluid still moves inside the bottle, so the spots are very big.
Right?
Yes.
It shears. Okay. I guess, there are some other more viscous fluids such as
yes, I could use glass.
Glucose. I guess that's
we
not
have the same behavior.
So, can we look at your motion time graphs for if we fill the water with water?
Sure.
Okay, can you tell me like roughly what so the oscillations here, yes, this is quite an interesting graph, you see. You have this sort of slower amplitude, slower frequency oscillation, superposed with higher frequency ones.
Yes.
So which one is actually the rocking motion?
This whole is the rocking motion, because we have two kinds of rocking in the water. We have first the rocking of the liquid inside the bottle and the rocking of the bottle.
Okay,
in the bottle.
so
we have two superposed.
So you have two important periods.
Yes.
Am I right? What are the values here? I think your long period is
this time and
your long period is about 1 second and your short period is about 0.1 second. A difference about 1 order. Okay. Yeah. So these periods, can you get them from your equations of motion?
No, because the flow in the water is chaotic, so we cannot predict this mathematically.
It's chaotic
yes.
for every case.
In the range we tested for
yes. What do you mean precisely by chaotic? As in
we cannot predict the exact shape of the fluid inside the bottle.
Okay. Okay. Thank you. Okay. Shall we look at okay, this is the problem we are tasked to study, right? Can you tell me what's the importance of filling the bottle with some liquid? As in, what we are studying here is the motion of the bottle.
Yes.
Due to its interaction with the liquid, right? So,
the liquid inertia plays a key role.
Is there something would you like to tell me something about how the liquid interacts with the bottle?
We can have a few situations.
Yeah.
First, when the liquid is no viscous, we have the liquid like this, the most energetically favorable. But when the liquid is viscous, it's all around the...
it tends to spread around.
Yes.
That's why you see it's quite difficult to do that. Okay, what I meant was, because the bottle's motion is influenced by the forces it experiences, right?
Yes.
And one of the other bodies that's exerting forces on the bottle is the liquid inside the bottle. So can you tell me the forces acting on the bottle due to the liquid?
It's the weight of the
the
liquid, so we have a torque.
No, so maybe at the point of contact between the liquid and the water.
We also have viscous forces.
Yeah,
and
you also have the pressure, right, due to the liquid?
Yes, we have.
So do you think that might be the most important factor in most important force exerted by the liquid on the bottle? I mean, yes, you said that the liquid has weight. That's definitely
That is
true.
the main
so,
force that the liquid has.
Yeah. So the weight of the liquid is exerted on the bottle through its contact, which is through pressure, right?
Yes.
So and the
But
pressure of the liquid on the bottle depends on its shape.
it depends on the shape of the bottle.
Depends on the shape of the liquid.
Yes, it depends.
Yeah. So
We cannot.
maybe it might be. Do you think it might be better if because looking at the problem, do you think it might be better if we make some simple models of how the liquid might look? Because okay, shall we look at one of your videos, like say for water?
We can see that the oscillations of water in the interface of it and the air is very big, the oscillation, and so we cannot really predict the shape because we have other kinds of waves alongside the water.
Yeah, there are waves, but you can see that the shape really does not shape. I mean, there's a difference, right? You have like glycerin where the liquid actually goes around, and this one where it more or less vibrates this way.
Yes, because
So do you think this,
low
the
viscosity.
vibrations, the oscillation of the liquid this way could be affecting, could be the cause of the oscillations of the bottle this way? Do you think?
This oscillation of the liquid causes torque. That in the torque varies its direction. So first we have a force to one side or the other side. So this causes the rod. The torque of the liquid causes the rod.
Okay. I think maybe if we have more time, we could study a little bit more detail. Okay. Now let's talk about your experiment. Can we go back to your position time graph?
Sure. This.
Yes, yeah, that's fine. Like we said earlier, there seems to be two periods over here, right?
Yes.
The long one and the short one.
But we cannot calculate these periods because they are
Okay, so-
not constant nor.
Okay, so what this position time graph means is that actually in your video, what you're seeing is the bottle is it is doing oscillations
Yes.
about a moving equilibrium point. Is that true? So it is. It is okay. So let's call the higher frequency ones vibrations. So the bottle is vibrating and translating.
Yes, we calculated the center of the bottle position.
I'm not. I do not doubt that. As in, what I'm trying to say is that your bottle is undergoing two types of motion at once. It is vibrating, the higher frequency, and it's translating back and forth about a single position.
Yeah,
So
that
do you
happens
think-
because
do you
of
think
the
that,
non-linearity of the liquid shape during
Okay.
the
So
movement.
do you think that could be due to the non-flatness of your
No, I don't think
No,
because
okay.
we can have because this is
So-
caused by the low viscosity of the liquid.
okay. Okay. Low viscosity.
Yes.
Right. About this. So in your opinion, which one is? If I had a curved if let's say my floor was not that flat, how do you suppose this graph would change?
The bottom will move very much, a lot more.
Like say okay. So
The graph would be like this and this. Yes.
let's say okay. Now we are thinking that the ground is flat, right? So the
Yeah.
bottle just moves left and right this way. If let's say there was a small not part, can we look at your video? Okay, let's say there was a small this is yeah, okay, so you see the bottle is vibrating
Yeah.
and moving back and forth. So if we look at the ground very closely and somehow we realize that it is actually this slightly curved shape rather than this shape. If you go back to your graph, how do you think, do you agree with me that the long periods will have a greater amplitude?
I would say that the graph would be like something like this or
Okay, thank you.
not that.
Okay,
Okay, yeah.
thank you.
Thank you.
Can you return the graph where the two oscillations that you said you could, because you
explain what oscillations, which oscillations are which? So which one is the bottle oscillation and which one is the liquid oscillation?
Okay, yeah. Actually, what I had in mind when I was during the discussion was that the bottle's rocking oscillatory motion actually refers to the higher frequency.
Sorry, quickly.
Yeah, the higher frequency ones, not the long period ones.
So you're saying that the higher frequency oscillations are the bottle oscillations?
It's the bottle's rocking, yeah.
And this is the water oscillation?
The longer ones is the bottle translating, which is the rolling.
Next question. What happens if the initial push is, well, if you push it so that the initial velocity is very high, like if you kick it only precisely, like imagine it's precise but really big force.
We'll have the liquid rolling in the bottle.
Okay, so.
But after a long time, when the bottle would,
Right, I understand. Okay.
the bottle will also rock.
Do you agree?
No, okay, yes, it will roll forward first, but towards the end, I agree that towards the end it will rock, but maybe we will observe better rocking motion.
Yes, I'm just interested. Will it still oscillate or first go around the bottle and then oscillate?
It depends really on how hard you kick it.
Okay, okay. Then, did you consider the waves? So, it's still a liquid. So, what effect does waves have in liquid?
The waves have the effect on the smaller oscillations. So we have the period, the oscillation variations due to these waves.
And how do you think? What effect
Yes, I do agree that the waves, the change in shape, which is the waves out on the water surface, is actually the crucial factor in determining the rocking motion.
And do you also think that these small oscillations are caused by the waves?
Yes, I do think they're caused by waves, and I think that's a key importance in this.
About the energy distribution, I'm really interested, and this question also goes to both. So, is the energy distribution to the liquid and the bottle like constant, or does it change?
It changes.
How?
There are energy dissipations due to the viscosity of the liquid.
No, not that question. Assume there are no dissipations. So, would the system go, would the liquid go with one constant energy and the bottle with the other, or would the energy transfer from the liquid to the bottle and then from the bottle? Then first she and then.
If you have the whole system, energy would be constant. So,
I think what you described is actually true because the liquid inside actually rises up and down, so its gravitational potential is changing.
So are you saying that the liquid would have one constant energy and wouldn't change
No,
during the process?
I'm saying that the energy of the liquid in the bottle actually feeds into each other.
Thanks.
Yeah.
Perfect, thank you.
First, I would like to thank you for the good discussion and thank you for the review. And for my final considerations, I would like to say that the period variations and the approximation for the underdamped are only for very viscous fluid. And in the range we tested with water, it was not possible to have a very high viscosity. So the damping is not linear. And the main oscillations are due to the changes in the center of mass of the fluid inside the bottle, and the secondary because of the oscillations in the surface of the liquid. And the graphs were explained in a satisfactory way just for our understanding of the phenomena. We cannot take quantitative data from those graphs because we have a lot of varying parameters when we vary the velocity along the movement. So we have variation on the viscosity, variation on the flow. We can have vortexes or other kinds of waves along the bottle that are very hard to explain mathematically or even physically. And I evaluated other parameters than the amplitude, like the period, that I consider much more important because when you have an underdamped, the period is constant, and in our graphs we could clearly see that they are not constant. So, the energy question that you said, I would like to say that if we don't have dissipation, we would not have rocking because the fluid would be non-viscous. So in this case, when the viscosity is equal to 0, we have no oscillations. So it always dissipates energy. And thank you very much for your attention.
Thank you.